So without further delay, let's get started. Today, I'm going to talk about my work on robot motion learning with physics-based PDE priors. So first, let me introduce what is the problem of motion planning. And motion planning is a way for an agent to coordinate its behavior from a given start to a given goal while satisfying all the desired constraints. So whenever a dynamical system or a robot need to move, they need to solve this motion planning problem. Okay, and it has application, or these are the applications that my lab focus on, ranging from full body motion planning. Here there is a mobile rugged robot. It is moving objects from a given start to a given goal. Then we also solve this problem in dynamic environment where we dynamically place obstacle in front of the robot. Another area that we are very interested in is in reactive manipulation. While robot is solving manipulation planning problems under constraint, they may experience some disturbances. How robot dynamically adapt to those disturbances and continue to solve the assigned task. Lastly, we are also applying these motion planning tools to reactive multi-agent planning, where you have large number of agents. They are performing their assigned task, and then they will have to reactively avoid collision with each other. So spreading across all these problems, the core issue is how to solve these motion planning problems, how to come up with tools that are efficient. And the focus my lab has is on developing these tools that are real-time, that enable real-time coordination of robot movement in unstructured constrained environment with minimal pre-training or trial and error. I have been trying to solve or achieve this objective for quite some time. During my undergrad, I started with sampling-based motion planning method, and my focus was on coming up with adaptive sampling techniques so that these sampling-based method can construct their tree as quickly as possible. Then one branch of that tree is your path solution from your start and goal. And then during my PhD, I moved toward extending these methods to data-driven approaches. So the issue with classical sampling-based techniques were they were computationally very slow. As the robot dimension increases, let's say you are planning motion for a humanoid robot, it's a huge degree of freedom. For those kind of systems, their computation time became very slow. So we could not do many real-time applications because of the slow computational speed of those methods. Then I moved toward data-driven approaches. In 2018 or 19, before that, many people were trying to solve motion planning problems with these neural networks, but they were missing one key piece. And in these papers, I gave the recipe that just having neural network is not sufficient. You can do imitation learning, and still it won't learn. You need stochasticity in these models, and you can incorporate stochasticity in different ways. In our work, we use dropout. Then people took up that idea, moved toward using variational autoencoder. Now you use the diffusion model. They have some sort of stochasticity. They start with some noise and then denoise it over time. So there is some sort of randomness incorporated into the process that helps these models plan motion. So the core recipe is you need neural network, then you also need some sort of stochasticity in the process, so that because these neural networks, they are approximating the solution, they can get stuck into local minima. This denoising process, or starting with some multiple seeds, you basically help these neural networks come out of those local minimas. Okay, but my main issue with these models were the training cost. So offline, we had to run these classical methods to gather all the data. And then you were training these models on that data. And yes, during inference, it was giving fast inference. But if we think about it, were they really solving, overcoming these slow computational speed of these methods? Because if you add the training time or time spent on getting the data and then combine it with inference time, you may think that it's not really beneficial. So when I started as a faculty at Purdue, I started looking at some other ways to train these neural networks without expert demonstration. And there are three features that my lab focus on. Like one is inference efficiency. I want to develop a method that allow immediate execution. They infer plans as quickly as possible. Then second feature that we look for is training efficiency. We want to reduce model training cost. We want to eliminate need for expert annotation. And this will facilitate transferability. Like right now, whenever you talk to someone who is doing imitation learning or training very large models, the second question come up, can they transfer to a different environment or unseen environment? Because the issue is when you move to a different environment, you may need to regather all the data. But if you have a model whose training cost is very low and that eliminates need for expert demonstration, then you can transfer that model very easily to a new domain. Third feature, which is very important, like we want to design these models so that they adapt to high degree of freedom, very complex terrains, unknown environment, or very complex constraint like involved in manipulation problem. And they should also scale to large number of agents so that we can deploy multiple robots operating in a given environment. Then they can solve some task in a coordination or in a decentralized manner. So just to give a overview, like where we stand in terms of these features. So we have optimization-based techniques, and these techniques, they have high inference efficiency. We have very nice optimization-based tools that can find a trajectory very efficiently. They have very high training efficiency. You don't need to pre-train your optimizer, but they do not adapt to very complex scenarios. They are prone to local minima, and they can often get stuck there. Then we have like a classical tools for solving robot planning and control problem. We have like discretization-based approaches. You may know A-star, you should. And then there are sampling-based approaches. There are other classical tools within control, like random shooting method and techniques like that. These methods, they have high training efficiency. You do not need to train them, but their inference efficiency is very slow because these methods, they need to either discretize your entire space or construct a graph and then find a path through that. Recent advancement, I should acknowledge that people are exploring like how can we use massive parallelization within these methods to speed up their performance. But we still have to see how these methods scale to complex kinematic constraints. Then we have data-driven approaches like imitation learning or reinforcement learning. We know they have like very low training efficiency, but once trained, their inference efficiency is very high, and they also adapt to very complex scenarios. But can we have a method, like I have mentioned all these three categories, they were missing either one or more of those features. Optimization-based, they could not adapt to complexity. Sampling or classical method, they had like low inference efficiency, and then data-driven, they have like very low training efficiency. Can we have method that have all these three features? So our answer is yes. Like if you incorporate some priors that are available to us from physics, you can achieve all these three features. And that will be the focus of my rest of this talk. So one question that come up, like when I say we use physics priors, like what physics priors to use? Okay. Often people confuse this physics prior with a physics engine or a simulator, but here in my talk I specified very clearly like we use PDE priors because I was getting this question again and again, but where is the simulation here? So it's not a physics simulation, it's a PDE that we use as a prior. So when we discuss PDEs, one PDE that is you may have heard is HJ PDE, Hamiltonian-Jacobi-Bellman equation, and it governs the motion of some dynamical systems. But that PDE is very hard to solve. It has like singularities, multimodal problems, and then when you apply both kinematic and dynamical constraints, it becomes very difficult to solve. Then we analyzed that equation and we said if you assume trivial dynamics, that equation boils down to this econal PDE. So this econal PDE has two functions. One is this t, and other is that s. So t is an unknown function, and it is a value function. We want to solve this PDE to find this unknown function t. S is a known function, and it is basically, it defines your constraints. So it could be distance to obstacles. So given the configuration of the robot, let's say QS, this S will tell me how far my robot is from the nearest obstacle. Is that clear? Or I can even change that constraint to something else, like instead of having a distance to obstacle, it could be distance to nearest manifold. Okay? It could be manipulation manifold or something. So this S function is known. I want to solve this PDE to find this T, which is a value function. And once you solve this equation, it gives you these wave fronts using which robot can navigate from one point to another. So given this source point, you solve this PDE, it gives you this travel time function, which is this T. This travel time function is also a value function. So just following the gradient of this T, you can navigate to any point in the environment. So numerically, there is a method called FFM, fast marching method. It solves this PDE, but it's a numerical approach. It cannot scale beyond 3 dimensions. So when we studied this PDE, our main interest was, can we scale it beyond 3 dimensions to actual complex robot systems? So neural network gave us like a possible way, like we can, instead of using numerical solver, we can use neural network to solve this PDE in high dimension. So the first work that we did, you have this neural network that tries to solve this econal PDE. So the input to this neural network, so this neural network is a black box, but we put structure into this neural network that respect the properties of this PDE. I will briefly discuss that, but if you are interested, check out the paper in order to understand the structure of this neural network. But for simplicity, I will assume it's a simple black box neural network that take robot start, QS, robot goal, QG, and environment perception as an input. The output is this travel time function. So this is an unknown function, so I want to train this neural network to solve this PDE so that once trained, I have this accurate or approximately accurate travel time function. Now, the way we train this model is you give this input and it predicts this travel time. Then econal PDE says if you take the gradient of this travel time with respect to input, QS in this case, this is equal to inverse of your constraint function. So this PDE is giving us some structure. So the training becomes very simple. So you sample bunch of robot start and goal configurations. You have environment perception. For each of these pairs, they go through neural network. You predict their travel time. Then you backprop to compute this approximated constraint function according to your econal PDE. Then your yes.
Do you have a question? So how do you encode the problem in your efficiency? Is it within S here or?
That's a good question. I will come to that in a moment. So QS is, in this case, so the motion planning problem is defined by robot start, goal, and environment perception. Right? Standard motion planning problem, you give it to classical method or optimizer, it takes the start and goal and your environment like distance to obstacle or whatever observation you have available. Right? So that's define the problem. And in this case, we are giving only this problem set. So QS and QG and environment perception goes through neural network and you predict this T. Then the way we train this neural network is through gradient matching loss function. So we backprop, compute this gradient with respect to QS, and then econal PDE says inverse of this gradient norm is basically your constraint function. Okay, so we approximate this constraint function and compare it with ground truth constraint function, like your ground truth distance to obstacle. Is that clear? So the loss function is on the gradients of the neural network. It's not on the forward pass and then you compute some output and then you define. The loss function is on the gradient of the neural network. Yes?
Question. Could you clarify about the output of the neural network case and how do we use the output to gather the desired poses of the robots or reach a
So yeah, I will come to that shortly, but that's a very good question. So the output in this case is a travel time, T in this case. It's a value function. So in order to get the gradient, you just have to follow the gradient of that value function and it will give you a trajectory. Okay? So we use this simple gradient matching loss function. So if you think about, the only data that I need is randomly sample start and goal and their distance to obstacle. That's it. So this is your standard motion planning tool. Is like if you use, for example, sampling based method like RRT or RRT star, they require some clean checker and way to randomly sample your configuration, and then they have some machinery to find the trajectory, right? Our data is similar. We are requiring randomly sample robot configurations and their distance to constraint or collision in this case. And then we use that constraint function as an expert to train our model, because our neural network gradient leads to approximation of constraint function, and then we compare this approximated constraint function with actual. Does that answer? So theoretically, it all sounds simple, but when we actually applied this, we could not scale this method beyond 4 dimensions. So numerical solver was solving it for 3 dimensions. We showed that, okay, we can do 4 dimensions, but numerical method could also do 4 dimensions. It was just a little bit faster. And then we started investigating, like, what's the issue? And we found out there are 2 main limitations. One, there is like Econal PDE has multiple solutions, and our neural network is unable to capture those multiple solutions. So it is suffering from that multi-model problem. Second, because I am training this model on randomly sampled start and goal, the gradient between my consecutive configuration remains uncontrolled. But if you think about the trajectory, it's like you start from start, you go to next configuration, then you go to next configuration, and it gives you a trajectory. So if my gradient between my consecutive configuration remains uncontrolled, it can lead to error. And I will show you shortly like how that looks. So these were the 2 limitations we found that we thought is basically limiting our model from scaling beyond 4 dimensions. So the first solution we explored, like, can we use viscosity Econal PDE? So one of the problem I highlighted, Econal PDE has multiple solutions. So if you add this Laplacian, then this Econal PDE has a unique solution. And that did lead to like much better performance. With this model, we were able to scale to up to like 6 DOF robot arm. And it could plan motion in very narrow passage. But this viscosity Econal PDE came with a cost. So now I have this double derivative of neural network with respect. So I have this Laplacian. So that was very computationally expensive to compute, and training cost went very high. So that again was against the objective that I wanted some model that is very fast to train. But this viscosity Econal PDE did lead to better performance. However, we still did not do anything to regulate the gradient between my consecutive configuration. We still trained this model on randomly sampled start and goal. There was another technique that we proposed along the way, that you can approximate this Laplacian with Dirichlet energy minimization. I won't go into the detail, but if you are interested, check out this paper. It's a recent IROS publication. So it discusses like how can you use Dirichlet energy minimization to approximate Laplacian as you train your model. That's a cheaper approximation of this Laplacian. Still, it takes a lot of iteration to train because you are over time approximating this Laplacian. So at the beginning, your model will perform very bad. So coming back to those properties, that it has multiple solutions. And it has like, and the gradient between consecutive configuration remains uncontrolled. We found out that solution to these problems rely on within the properties of Econal PDE. So Econal PDE is a geodesic distance. The solution of Econal PDE is a geodesic function. So it should respect the properties of a geodesic distance like triangular inequality, and there are different properties of those geodesic distances that it should satisfy. And geodesic distance, it also has like multiple solutions. It captures multiple geodesic. Like for example, if you have start and goal, I can either go this way or I can also go this way. So there are multiple solutions available, and all of these solutions may also be shortest travel time solution. So there could be some symmetry in your configuration space or something. There could be multiple solutions. All of them can be equally relevant. Second property is that the solution of econal PDE is a value function. So it should satisfy Bellman principle of optimality that I will discuss shortly. So let's start with first property. The solution of econal PDE is a geodesic distance. So we should use a metric learning that enforce the prediction to a valid metric space so that we respect all the properties of a geodesic distance. So we should ensure consistency with geodesic distances. Like it has symmetry property, it has triangular inequality, like your path, straight line path between start and goal, and your path through some middle point, the length of that path should be higher than the straight line. Okay, so that's the triangular inequality. So this geodesic distance, neural network should satisfy that property. So we propose this structure for this neural network. What this structure is doing, before we were doing this, so consider this problem. I have two paths from A to B. If I just use L2 norm in my loss function, it will squash them into this straight line. But if you use this this structure that we have, it is taking your QS, pushing them to some latent state, and then it is applying some max pooling on them. So what it is doing, it is piecewise approximating this solution. So you see, you get this diamond shape approximation of your path. Instead of the circles, you are piecewise approximating all those multiple solutions. So this metric learning here, it takes your QS and QG, pass them through some neural network, and then it does something with the latent features of those QS and QG, like it applies this max operation, and then it applies this infinite norm on that latent encoding. So if you think about it, we move this start and go to some latent space and then learn the geodesic distance in that latent space. Is that clear? Okay, so that was the first change we did. Second, the solution of this econal PDE is a value function, so it should respect Bellman principle of optimality. And then we found out this can solve the problem of over gradient being uncontrolled between my conjective point. So think of this simple econal PDE. So it is absolute function. So I have this absolute function, and the way I am training my neural network is to randomly sample those green points. So if I train my neural network on those points, it will only minimize loss function on those points. It won't do anything on those segments. So for that neural network, both functions are accurate because my error on those green points is 0. But if I have little bit jump in between them, my neural network is unaware of that because I did not do anything to regulate the gradient between those conjective points. But if you think of robot trajectory, it starts from one point and then you keep going. If you have these little errors in between, your trajectory can go away from your desired goal. Does that make sense? So we had to regulate this gradient so that these bumps that you are seeing, it should capture this absolute function. So the solution to this problem is by treating econal PDE solution as optimal value function, and it must satisfy Bellman principle of optimality. So when we say it must satisfy Bellman principle of optimality, we have to do temporal difference learning. How many of you are aware of standard Q learning, deep Q learning? Some, like most of you are aware. So in Q learning, you have your reward function, Q function at your next state, next action, minus Q function at your current state, current action, right? So that's your Q learning. And it came from your temporal difference value, like value function. You have reward value at next state minus value at your current state, right? So this equation is similar. We show complete derivation on how we arrive at this equation, but the main point is this is a value function. So you have your QS. We perturb that QS towards some direction. So we have value at next state plus some reward and value at your next previous or your current state. So t is a value function. We perturb over qs in some direction to get the next state. So this is value at your next state. That's value at your current state, and this is the cost function, which is inverse of your constraint, whatever you give, like it's a distance. So if I want to minimize or maximize distance to obstacle, so that's your reward function or the cost function. So when you combine this temporal difference learning, so in our paper, we show how you can analytically compute this u. So how can you perturb this qs in a direction that will give you the next conjective state? So basically, this u is, short answer, just the gradient of your travel time. So you move a small step to in the direction of your gradient of your travel time. So that's your next state. Okay? And we can analytically compute that gradient. So then we combined our gradient matching loss with this TD loss, and then this model was able to perform really well. We were able to scale it to very high dimension problems that I will show you shortly. So first, on a very simple problem, so this is maze-like environment. If you combine your our approach like gradient matching loss with TD learning, you get these kind of contour, and you can see it is matching this expert FFM. It is a numerical approach. It can only go till 3 dimension, and if you have a very good computer, it can do 4 dimension. But you can see time contours are almost similar. So when you do this neural network approach, it can capture similar solution. However, these are 2 methods. It's our first method. It was without any TD learning or metric learning. You can see the gradients at the source at the beginning are very good, but as you go far from your source point, the gradients start becoming very bad. So the error between your conjective states start propagating and everything goes wrong. And this is viscosity econal PDE. It still has better solution than this one, but still it did not regularize gradient between my conjective states. So still there are some artifacts that you see in that plot. So combining gradient matching with TD learning leads to like much better result. So now I will discuss one by one inference efficiency, training efficiency, and adaptability of this model. So let's start with inference efficiency. So this is on a simple 7DOF setup. So overs, you can see it's like takes 0.07 second to find that plan. And this is MPyNet is from NVIDIA. It was trained on huge amount of data. I will show you. It took them several weeks to gather that data, and it took them 1 week to train that model. Compared to our model, it took us, I think I will show you, less than a minute to gather data, less than an hour to train like this model on 300 environments. So this is one model generalizing to 300 different environments. Still MPyNet and overs, you can see success rate are very similar, and planning time is much faster in our case. And for lazy PRM, these times only show graph query time. We did not count graph construction time. So we pre-constructed the graph and then used that graph to query the time. Then it also scaled to like a very complex indoor environment. So this is multi-floor environment, and success rate, again, you can see are very high, and planning times are very low compared to like other approaches. So there is a difference, like because it's a value function, you can incorporate this value function into MPC or MPPI. So any available tool that can use your value function, you can even incorporate it into trajectory optimization. So we show if you combine it with MPPI, it is much faster, because then you don't need to compute the gradient. You just use the prediction directly, the cost to go or the value function output. But this gradient, you can also use the gradient of this travel time to find the trajectory still. the computation time does not increase significantly and the success rate is high. And then we were able to scale it to 12 DOF. This is a very complex environment for these models because it has very thin obstacles, and these PDE solutions struggle when you have these thin obstacles. So we specifically picked this environment to show it can nicely capture these thin obstacles and still do planning. This is 15 DOF. And this environment is particularly challenging for this robot. This robot is very huge and this room was very small, so it's a very confined environment for this robot to be able to move from one point to another. So that's about like inference efficiency. I showed you these models, like as you scale to high dimension, they retain their computational benefit. Now my favorite slide, I want to talk about training efficiency. So these are different environments. So if you just pick this 7 DOF environment, for that environment, it took like several, for us, it took us 50 minutes to gather data. So per environment, it was taking few seconds. So multiply by 50, it took us like 50 minutes. Training took 46 minutes compared to, and we compared it with MPyNet. And these numbers are taken from their paper. It took them several weeks on a large amount to gather large amount of data, and then 1 week to train. We trained our model on one GPU, standard 3090, but MPyNet was trained on 8 NVIDIA Tesla GPUs. So it took a huge amount of compute power to train that model. And these Gibson environment, like you can see, it takes 24 seconds to gather data, 9 minutes to train. So what I want to highlight here, when you use these PDE priors, you have like much higher training efficiency. Like the way I see, physicists gave us these physics models that govern some dynamical system. Now we are regathering the trajectories, ignoring these models, just to reproduce these models. Okay, so why not just use them? They are there, and if you use them, you will have very high training efficiency, you will have very high inference efficiency, and these models can still adapt to very complex environment. And these models are transferable. So when I started this research, our models were training like 2 days to train. Like training would go 2 days, because we were not satisfying properly the properties of these PDEs. But with these properties we satisfied, it came down to like less than an hour. And my lab is still pushing further to go beyond that. Like we are still in preparation for a paper. I think our latest model, like on 12 DOF, it takes like less than 5 minutes to train. So it's much faster. Yes?
Constraint that you have in like the S function, is that only just the travel time, or you have other constraints?
No, S is the constraint function. It's a distance to collision. Yeah. So it's not a travel time. Travel time is t unknown function given this constraint function. So we solve that PDE to find this travel time.
And also, is the model architecture between, I guess, like between like the MPyNet and your paper, how different model architecture?
So our model architecture are very different. So our model architecture is designed to respect some properties of econal PDE. For example, I will give you one property, like it has the symmetry property. So travel time from your start to goal and travel time from your goal to start should be same. So it has the symmetry. And our architecture is designed to respect that symmetry. It enforces that this value function respect. And then other thing I mentioned, our value function is a geodesic distance. So architecture is designed to respect those triangular inequality and those kind of things. Whereas MPyNet is a standard architecture that we usually use for large models. Yes.
So I think it's a very good idea to apply econal PDE for a manipulator task, because I see in the econal PDE you don't have the dynamical constraint in it. So in every state, you probably assume the manipulator can move with any direction. But in reality, it still has some dynamical constraint, and you have singularity in the manipulator. So have you experienced any?
So that's a very good question. So currently, we like in this work, we consider kinematic. We have a paper accepted at NeurIPS this year where we solve kinodynamic problem with these econal PDE. And we basically show that these econal PDE can still regularize the solution to HJ PDE. So you can think of precondition of warm start to some HJ PDE solver, and we showed like some kinodynamic, like on a humanoid task, like how we can do context-rich locomotion, and we also showed manipulation, if I remember correctly. But in second point, you pointed out to something else as well, like manipulation. I'm coming to manipulation shortly. Yeah. Yes.
Just wondering, when do you need to redo the data generation and training? See the bottom channel, the location of the obstacle to will train.
So in this case, yes. So we have I will discuss one more work, like we can selectively retrain neural network. Like I will show you how you can select parameters that you need to retrain if some part of the environment is changed. You do not need to retrain everything.
Cool. So and the Apple training,
You can give the arbitrary start and the ball location.
yeah, right. Okay, cool.
Yeah. So far we have discussed training efficiency, adaptability to complexity. Like I have shown you that it scales to very high dimension, but I want to discuss like how it can scale to manipulation or very large environment. Neural network has this problem, like if you have a very large environment, it struggles. It suffers from spectral bias issue of your neural networks. So first, to scale it to manifold or manipulation problem, all you have to change is your expert speed function. Instead of distance to obstacle, make it distance to constraint manifold. Like if, for example, you are doing door opening task, that's one manifold. And if you can compute the distance of robot configuration to that manifold, you can use that as a training function. And then we were able to solve this, like, so this model is like opening door, and then it will move that cup without tilting from one point to another in this confined space. So again, you can see computation times are very low, success rate is very high, and we compare it with C by RRT, which is a sampling-based approach. CompNetX is a data like imitation learning-based approach. So CompNetX I proposed during my Ph.D. To solve these manipulation problem, but you have to gather data using some C by RRT or classical planar to train that model. And then question come like, how can we scale to multi-model problem? Like, for example, if you have this cup, you are moving it, keeping it upright, then you are tilting. These are two different constraints. And then this robot also need to open cabinet, retrieve something. And if you are doing steering, so that spoon motion is one manifold, then steering is another manifold. If you are doing hammering or all your tool manipulation, they are multi-model constraint problems. So how can we extend these methods to solve those multimodal constraints? So the solution relies in classical PDE literature, like if you study classical PDE literature, they used to represent PDE solution as a sum of finite basis functions. Okay, so if each of these basis function represents a manifold, then I can combine them to get my global trajectory. So this is what we do. So we decompose our problem into, so this is just for depiction, think of this 2D environment. I can break it down into multiple pieces. And then for each piece, I can learn some basis function. And then I can combine the basis function to get my global value function. But there was a challenge there. So I want my value function to be continuous, like fully spatially connected, because in trajectories, if you have these decomposition, you can have singularities at all of these partitions. So how can we get this global value function so that I can go from any point to any point, from this segment to that segment, without experiencing any discontinuities or local minima? So that was the challenge, and then we proposed some architectures. If you're interested, you can go into the details there. But this architecture basically decompose your problem into subdomains and then learn this global function. So that addresses your question, like if some part of the environment change, you don't need to retrain everything. You just need to retrain that basis function. And that's very fast. So we were able to scale it to very large environments, and it still retained like very high success rate. Another advantage of this decomposition, you need fewer parameters compared to your end-to-end function. So that's what we found. And then this is like on a real, our campus, like this robot is navigating these multiple narrow passages from one point to another, and this entire environment was decomposed into multiple basis functions. And then the same idea applies to your multimodal manipulation. You have multiple manifolds. You can represent them as basis function. You can combine them to get trajectory. So this is one neural model doing door opening, and then it will retrieve this cup without tilting, and then it will do this pouring task. We recently moved to humanoid robots, so all these tasks are being solved by humanoids. So this decomposition is also on the space, so a robot can move anywhere in the environment. So that's decomposition on the plane. Then we have decomposition on the manifolds. So all these like multi-model problem is being solved, and this paper, hopefully we plan to submit to a conference very soon. But we can solve multimodal manipulation problem that you see very popular with imitation learning or data-driven approaches nowadays. We can solve all those problems with these models. Another area that we extended to like unknown environment. Right now we assumed we know the environment, and then from that environment we computed the distance to obstacle. I need to speed up. So one thing that we think the motion planning problem is computationally expensive is because your mapping feature is not good for motion planning. There is a huge gap between your mapping features and your motion planner. Like you have the sign distance field or occupancy map that necessitate the building of some computationally expensive tools for motion planning. Like for example, to translate those maps into C space, you either have to use sampling-based technique or optimization. Then you find a trajectory in your C space. So can we have a better mapping that does not require this very complex tools? So answer is yes. If you can learn maps as a travel time function, then you don't need any planner. You just follow the gradient of that travel time, and it will give you a trajectory. So we investigated that. So as your robot explores the environment, it gets the depth perception, and you can locally approximate your constraint function. So as your data is coming, you can train this model. So here, this video is showing that robot is exploring the environment. Perception is coming in stream, and it is building this arrival time field map. And then once you have this map, you don't need any motion planning tool. Just follow the gradient of this map. It incorporates that geometrical representation that helps robot navigate the environment. And so over this paper, the mapping time was twice than standard mapping like occupancy maps, but our latest model, we were able to reduce this time by like 40%. So each time, like in each frame, neural network just take 2 seconds to train in this case. But our latest model, I think it takes less than 1 second to train as robot explores the environment. And it even scales to like, so this is a rare robot mapping this environment. So you can see as it is exploring, it is training the model on the fly and to get those travel time. So if we can get these maps in almost same amount of time as your occupancy map, then you don't need any motion planner. You can just deploy your robot anywhere in unknown environment, and it will figure out how to move in that environment with these plug and play models. And another advantage of this, like you can even do manipulation with it. You can equip robot with your in-hand camera, and it will explore and construct these arrival time field maps in C space. And still, yet it can still like navigate. So we show that in our TRO paper. If you are interested, check this out. Okay. So this is like the robot arm setup we had. It was using this in-hand camera to construct this arrival time field map in 6-dimensional C space. Another area we are interested in, like how can we solve these PDEs for multi-agent settings. So basically, instead of like HJ PDE, you basically solve HJR. You may know work from Sumel Benson here. And the way we differ from his work is like we want to push the scalability of this method to very complex robot manipulator with very complex geometry of obstacles. And this is one of our work, like here robots are trying to reach their target while reactively avoiding collision. We also scaled it to like assembly line tasks where multiple robots are performing their task while avoiding collision. So if you're interested, like check out this work. So in conclusion, if you should use physics priors because it gives you all these three features: inference efficiency, training efficiency, adaptability. In our future direction, we want to improve our training efficiency. Our current models take like 5 minutes. I want to achieve like real-time training. So that this neural network will be a plug-and-play model. That's my vision. Like if you have this plug-and-play model, transferability, generalizing to new environment won't be an issue, because the robot can just go there and train on the fly and perform all your manipulation, motion planning problems. And other areas that we are interested in is reactive, because these methods are very fast. So if they can generalize to very different settings, even if you disturb the environment, they can still recover from it very quickly. And this is like a multimodal problem, like where robots are planning for grasp and manipulation together. So that's another area that we are extending. This is a new problem I recently got interested into. It's called assistive manipulation, where robots are manipulating human body to do different tasks. Like for example, assisted dressing is a manipulation problem. You have to respect biomechanical constraint in order to move human body. I think it's a very nice motion planning problem to study, and we are extending these methods to those domains as well. So this is a bed wiping task in a simulation, like robot is moving human limb from one point to another, and other robot is wiping the body. So with this, I will conclude. I'm almost on time. So this is my lab. So without them, nothing would have been possible. So if you are interested, check out our lab website. And that would be it. Thank you. Any questions? Yes.
Thank you for the great talk. And I just wanted to ask, how would you compare like your method to say some of the other more recent motion planning methods, like say geometric fabric or drop complex set, in terms of like say reactivity or handling environmental changes? What's your opinion?
So graph or convex sets, like I think there are assumptions these methods are performing, like for example, having a convex obstacle. So that's one of the assumptions, like for example, if you see, what's the name of that? There's a Kurobo. If you see how Kurobo works, they assume robot and environment is represented with multiple spheres. And then they solve motion planning problem very fast. Okay, and even these parallelization, like their test work on parallelization, they heavily rely on this spherical representation of the robot and environment, and they solve this motion planning problem basically in workspace. But there is an inherent issue there. Like if you are solving this problem in workspace, a lot of current work, like in imitation learning, they are solving this problem in workspace. There is no guarantee that you can map this trajectory into C-space trajectory. Your robot may run into local minima. Oftentimes, like if you are performing very complex tasks, you will see that you don't have direct mapping from this workspace trajectory to C-space. Like if you really study motion planning and check out the literature from early 1990s, they were doing workspace motion planning. Then they figured out this is the problem, and then they moved to C-space planning. Unfortunately, we are going back to workspace planning. So these latest methods, they are very fast, but they rely on these assumptions, which eventually will lead to problem of mapping to C-space trajectories.
I don't think either are on the exposed space net.
So Geometric fabric, I'm unaware of that, but I think the other paper you mentioned, they assume fair spherical representation. No? Maybe I'm thinking of some other paper then. Yeah, I'm then not aware of that.
I guess like maybe for like geometric analysis things, could be like
Sorry?
so basically you model your system as a dynamical system, and then you try to essentially extract low vector fields.
Yeah.
Up and on and out. Like I guess maybe in that sense, like it would also be an
Yeah. So
space. How does that compare to, let's say, trying to take outer functions?
So I think there's a very strong relevance, like our recent work that we submitted to NeurEPS. It's basically on kinodynamic, like how can you come up with these travel time fields in dynamic space. I'm unaware of work that you are discussing, so I cannot comment on their relation. But in general, we want to go toward vector field. But we want to go toward that without expert demonstration, without learning from expert data, or just by solving those PDEs. Okay, I'm unaware of what the work. Maybe you can share, and I will be happy to get back to you. Yeah. Any other question?
One problem I always have with the optimization is that if the ball is close to a constraint, then the solution can be pretty unstable. Like during the solving process, the kernel system bounce back and forth around the constraint. Does your neural motion planning has a similar problem?
Yes. So the way you sample data is very important. Like I think it's in our experience, like creating a curriculum helps. Like starting with a simpler problem and then slowly coming up with start and goal that are very far helps. And then another thing that helps is like having more samples that are near obstacles, because those are the areas where you have sharp features and you want your neural network to learn those better. So yes, so we do suffer from those problems, and having some adaptive sampling helps.
I see. But after you finish your training successfully, then it's equally shift to sample goal near obstacle or far away from obstacle.
If you are following the gradients, and because it's an approximation, it can go to local minima. But if you use this neural network as a value function and incorporate within some MPPI, then it helps overcome those local minima issue, and it does well.
I see. Yeah, cool. Yes, thank you. And there was
Yeah. Do we know what methods the commercial robot rankings use?
I think usually they are like, I don't know what they are using, but usually it would be some classical technique or some classical motion planner or something like that. I would assume that would be the case, but I